This is the second example problem that's at the end of the reading packet. We are going to determine the final temperature of a metal. Out of all the calorimetry problems, these are probably the most difficult. The algebra on these is definitely the most skill-intensive set of algebra, and that's why sometimes students find these difficult. You're going to know that you're going to have a final temperature type problem because the text of the problem is going to mention what's the final temperature. So we're going to kind of do a specific set of steps in order to solve these types of problems. However, like all the problems in this unit, we're going to stay organized. So the first step is to ID your variables. And you're going to do that by reading the text of the problem. Label while you go through, and that'll be helpful. If 32 grams of aluminum, so that sounds like a mass, grams, at 210, because that's a temperature, are added to 90 grams of water, it's a mass. I just read a second mass, so that's going to tell me a formula that I will be using. At 20 degrees C, that's my second temperature, what is the final temperature of the aluminum? Now, it tells me the specific heat of the metal is C, and then I also know the specific heat of water because we're functioning within the liquid water range. Specific heat of water is a known value. Because there's two masses, I'm going to end up using mc delta T equals mc delta T, which means I'm going to need to have a column for the metal and then a column for water when I'm organizing my variables. mc delta T. mc delta T. I know the mass of my aluminum is 32. The specific heat is 0.22. I'm going to hold off on my temperature for a second. The mass of my water is 90. It's in grams. Specific heat of liquid water is 1 calorie per gram degree C. And I'm going to hold off on the temperature here for a second. The problem doesn't tell us enough information to fully solve this. We have to infer some information. Now, when a hot piece of metal is put into some cold water, the temperature of the metal is going to drop. So just a quick graph of kind of what that would look like. The metal starts at 210, and the water starts at 20. The metal is going to cool down, and the water is going to heat up. And they're going to keep doing those respective processes until they reach the same temperature. Once they are the same temperature, heat can no longer be transferred. Remember that heat's transferred from the hot object to the cold object, so heat can't be transferred. This is the temperature we're trying to figure out. Because of that, we can use T as a variable, and since T is the same for both substances, we only need to do T instead of like X and Y. Since our delta T has to be positive, we need to think about what order we're going to put these T's into the equation. So since 210 is going to be bigger than T, we're going to do 210 minus T so that delta T will be positive. Since T is bigger than 20, we're going to do T minus 20 to make our delta T positive. Once we have all of our variables set, we can sub these into the equation. Plug into the equation. I'm going to omit the units to make the work a little bit more clear. If you did use the units though, all the units that would need to cross out will cross out. So mc delta T for the metal and for water. I'm going to substitute my values in. 32 times 0.22 times T 210 minus T. And that's going to be equal to 90 times 1 for the specific heat of water times T minus 20. So we're trying to solve for T. To do that, we need to start by combining like terms. So on the outside of the parenthesis, if we do 32 times 0.22, we're going to end up getting 7.04. And then that's going to end up being multiplied into the 210 minus T. On the outside of this parenthesis, we have 90 times 1, which gives us 90 times t minus 20. The next step is to distribute the outside numbers into the parentheses. So 7.04 times 210 times a negative t gives me 1,478.4 minus 7.04 t. That's going to be equal to 90 times t, so 90t minus 1,800. I need to combine like terms again. So I'm going to add my 7.04 t. I'm doing the opposite, so that crosses off. These will get summed together, and I'm going to add my 1,800. And when I combine those, I get 3,278.4, which is equal to 97.04 t. Finally, I need to solve for t, so I need to divide by the 97.04, which cancels that. If I do it on one side, I must do it on the other. So t is going to be equal to 3,278.4 divided by 97.04. If I do that, my calculator is going to give me 33.784. Based on the sig figs on these problems, because of the complexity with adding and subtracting a variable, I'm going to suggest that you just do sig figs based off of the numbers. So 32 has 3, 90 has 3. I would just go ahead and use 3. 33.8 degrees C is our final temperature. Make sure that this makes sense. Does it fall in between your two values? And it does. It falls in the middle. Also, you can plug this number into t. So 33.8 minus 20 gives you 13.8. 210 minus 33.8, whatever that value is. And then if you run the left-hand side of your equation, get an answer. Run the right-hand side of your equation, get an answer. Those two numbers should be the same.